Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture of this course on control systems. So if you recall, in the previous lecture we have already derived the expression for the step response of an underdamped second order system, and we've also specified certain performance metrics which we then promised we would derive in the next lecture, which is today. So let us without further ado get started with that. So to refresh your memory, we discussed about these performance metrics such as settling time, rise time, with which you are already familiar in view of our discussions on first order systems, but two new performance metrics begin to emerge as soon as you delve into these underdamped second order systems, which are this percentage overshoot and the peak time, and these are particular typical features of this underdamped second order step response. Okay. So let us try and derive some of these expressions subject to certain approximations if we can. Okay. So the first thing that we are going to try and derive is probably the rise time. Now if you recall, I had specified that the rise time can be defined in two different ways. One of the definitions is the time it takes for the step response to get from 0% to 100% of the steady state value for the first time. Alright, so that is one, which is time taken by step response to reach from 0%, so to reach from 0% to 100% of steady state value, right. There is also another alternate definition that people often use, particularly when the system is overdamped or critically damped, which is once again, let me call it T rise 1. Okay, so this is the original T rise that we are going to derive, and this T rise 1, which is a little more difficult to derive analytically. So we will just hopefully convince you that there is an approximate expression for this T rise 1 as well, but we will not get into the business of deriving this explicitly. Okay. So this T rise 1 is given by this time taken by step response, so typically of an overdamped or critically damped. So OD stands for overdamped, CD stands for critically damped. Overdamped or critically damped second order system, okay, to reach from 10% to 90% of steady state value. Okay. So it turns out that this first one is not very difficult to obtain analytically. If you just cast your attention on this expression that we have, which we derived in the previous lecture for the underdamped second order step response, then you see that what we are asking for is basically this: the first time that this yt attains a value of unity, right, because here we know that the steady state value is unity, all right. So what we then do is we just equate this 1 minus e to the minus zeta omega n t over root 1 minus zeta squared cos omega dt minus phi, and equate that to 1, right. So in other words, what we are saying is that we want this cos omega dt minus phi to be equal to 0 for the first time. Now of course it's a trigonometric equation, so it has infinite number of solutions. We are only interested for the first time that this solution is attained, right. So of course notice that we are ignoring these terms, these exponentials, because we know that only at t tending to infinity does this go to 0, all right, and we are not interested in that asymptotic behavior. We are interested in the first time it reaches the steady value, all right. So therefore we can say that cos omega dt minus phi, so recall that tan phi is equal to zeta over root 1 minus zeta squared. In other words, phi is equal to sine inverse zeta, all right. So this is going to be nothing but pi by 2. Of course I must write for the general solution, I should have written 2m plus 1 where m is an integer, but of course I am going to ignore that. I am just going to plug in m is equal to 0, because as I said, I am only interested in the first time that it attains this particular value. So then what do we get here, all right. So this is cos pi by 2. So therefore equating both sides, what we have is omega n root 1 minus zeta squared. Notice that this is nothing but this omega d times t is equal to pi by 2 plus phi, all right. In other words, t can be given by pi by 2 plus phi over omega n times square root of 1 minus zeta squared, which can then be written as pi by 2 plus sine inverse xi upon omega n square root 1 minus zeta squared. Now I am going to make the first approximation, and I am going to say that since it is a lightly damped or underdamped system, therefore I am going to ignore this xi and replace the sine inverse xi with a xi itself, okay. So we are going to say that it is almost equal to pi by 2 plus xi upon omega n square root 1 minus zeta, sorry not xi, it is zeta squared. So it is pi by 2 plus zeta upon omega n times square root of 1 minus zeta squared, and then subsequently make another approximation which might seem like an overkill, but you can actually try out with several different values of zeta between 0 and 1 and convince yourself that this is not a huge error. So what I am then going to say is that this is almost equal to pi by 2 omega n, all right. That is what we are going to claim. Now of course you will notice that there is a significant amount of approximation involved in this derivation, and you may not be very happy, but let me just convince you by saying that this actually works. In other words, what we are saying is that this rise time, let me call it Tr now, this rise time is inversely proportional to this omega n, all right. What is omega n now? Now notice, recall a few slides back, maybe quite a few slides back, when we had actually derived this expression. Let me go back there, right. So when we had this expressions, maybe yeah, so I had derived this here, yeah. So notice, what is omega n? What is so significant about omega n? Notice that the magnitude of the root is nothing but zeta squared omega n squared plus zeta squared minus 1 times omega n squared, which is nothing but omega n squared. So in other words, the magnitude of the root, okay, the magnitude of the complex number, whether it is a complex number or a real number, the magnitude of the root, okay, is going to be nothing but this omega n, all right. So in other words, what we are now saying is, in view of this new revelation, alright, the larger the magnitude of your roots of the second order system, the smaller is the rise time, that is the sooner the system rises in response to the application of a step input. Okay. Now of course you might say, okay, you define this rise time in two different ways, what about the second way? The second way, as I said, is more applicable for the overdamped and critically damped system, because of course they never really attain the 100% value until t is infinite. So for the general case without much thought, if you notice, this is almost close to 1.6 upon, again another level of approximation is probably 1.6 upon omega n. So in many textbooks what people generally adopt without loss of generality, I wouldn't say without loss of generality though, but yeah, so people are happy with a single unique formula rather than multiple formulae for the same. So you see, this is just a matter of this numerical value after all. So for the underdamped system we have kind of derived this subject to certain approximations on this zeta being small. We have shown that it is actually almost equal to 1.6 divided by omega n. So it turns out that with a lot of these plots and sort of an empirical computation, it turns out that for overdamped or critically damped system it also hovers thereabout this rise time. Okay. So in general people come up with a single expression for the rise time irrespective of whether it is an overdamped or an underdamped or a critically damped system, and that is almost agreed upon by most textbooks to be 1.8 upon omega n. I know this does not sound like much of a mathematical argument, but again there are a lot of empirical derivations or empirical data that is involved in arriving at this expression, so that should appear convincing enough for practical purposes at least. Okay. The idea to take home from this and to just embed sort of in your memory is that rise time is inversely proportional to omega n, which is the magnitude of the roots of the denominator polynomial, which is basically the poles of the second order system. Alright. Okay. So with the rise time out of the way, the next expression we are going to try and derive is the settling time. Okay. So again settling time needs a certain amount of modification, as I said, for an underdamped system. So how do we define the settling time? Settling time is the time taken by the step response of a second order system. So notice settling time can be defined for any system, not just for second order system. The reason I am writing this statement second order system here is because we are only interested in the settling time for a second order system. So let this not be sort of imprinted upon your minds that settling time is only applicable for a second order system or a first order system. Settling time can be applicable. These definitions, in fact, the rise time, the settling time, these are irrespective, these are agnostic to the system order. Okay. So the only reason I am mentioning second order system explicitly here is because here we have embarked upon a study of second order systems only. Okay. So I just wanted to clarify that. So that is the reason why I am mentioning second order system. But do not think that if you go beyond second order systems that settling time or rise time cease to make any sense. They still are applicable equally. Okay. So in general, if you just omit the second order system part, the definition will still hold. The time taken by the step response of a second order system to enter within a 2% band of its steady value and remain there thereafter. This is very important, and remain there thereafter. Okay, because notice this sketch we had drawn in the previous lecture. So as I had also clarified then, so somewhere here it enters the second 2% band, somewhere here it leaves the 2% band, somewhere here it again enters the 2% band, somewhere here it again leaves the 2% band. So these time instants do not qualify as a settling time value. Okay, the only time when it qualifies as a settling time value is when, for example, somewhere here for instance if it enters the second this 2% band here and then subsequently never leaves the 2% band thereafter and continues to remain there, then and only then does it qualify as a settling time value. So in order to do this, at the very first step we will make an approximation. What is that approximation? Instead of focusing on this actual plot which contains this cosinusoidal term, this exponential and everything, we are just going to focus on this envelope which I had written in blue here and drawn also in blue here, alright. So we are going to just focus on this envelope. So the first approximation is that this is an overestimate of the settling time. Why so? Listen, what we are doing here is we are saying that we do not care about the actual way in which this cosinusoid is making this response vary. We are just focusing on this envelope and the instant at which this envelope attains a value of 0.98 or this one attains a value of 1.02 in this case, of course, because 1 is the steady value here. If it is k, then it is 1.02 k and it is 0.98 k. Here k is unity, so it is of course just 0.98 and 1.2. So either this upper envelope has attained a value of 1.02 or the lower envelope has attained a value of 0.98. Since they are symmetric, they will attain these two respective values at the same instant. Okay. So either you equate this to 0.98 or you equate this to 1.02 and solve for t, that will give you the settling time. Now notice that the actual settling time is invariably lower than this or at most equal to this, because the actual response has entered this 2% band before, alright. In most cases you will see the actual second order response, alright, might have entered this band before, okay. So in most cases this will be an overestimate. Of course in some cases it may be an underestimate, so let me just zoom in on that portion so that you have a clearer picture. So suppose this is the upper envelope, this is the lower envelope, right, and let us say this is the steady value here, okay. It should be symmetric, my drawing is not very good, so it should have been symmetric. So for example, suppose at this point this is 1.02 and at this same point it is 0.98. Now it could be the case, let me use another color, okay, I do not have another color, so let me use black. So it could be the case that your system has actually sort of come in like this, yeah, and it has already, notice that it has already entered the 2% band somewhere here, alright. So in that case this is actually overestimating. On the other hand, there could also be a case where let us say your system has come here, alright, and it has maybe come at this point here, okay. So in that case you see it evolves like this, alright. So notice that in this case what happens, alright. So this is where you are estimating your settling time to be. So in the first case the actual settling time is probably somewhere here where it has already entered the 2% band. On the other hand, in the second case also you notice, so I stand corrected there, actually in all cases it turns out it will actually be an overestimation of the settling time, no, because you see even in this case it kind of evolves in this fashion and it goes like this. So here also it has actually entered the settling time, this 2% band, before the time when you are actually estimating it to be, alright. So in any case this settling time is always an overestimation, so we are on the safer side in that sense, right. So by approximating this settling time by only considering the envelope, we are actually on the safer side. So let us get an expression for this settling time now. So what we are going to say is that 1 plus e to the minus zeta omega n t s upon 1 minus zeta squared is equal to 1.02, alright. So in other words what we are going to say is that e to the minus zeta omega n t s upon square root 1 minus zeta squared is equal to 0.02, which after some simplification would lead to settling time being given by minus 1 by zeta omega n logarithm, the natural logarithm of 0.02 times square root 1 minus zeta squared. So up until this point it is an exact expression for the overestimated settling time, but at this point we will sort of notice that for zeta within the range from, let us say, 0 to 0.9, alright. For zeta within the range from 0 to 0.9, we will notice that the value of this logarithm here, ln 0.021 minus zeta squared, ranges between a value of 3.91 to 4.7. So in other words, this logarithm is not very sensitive to changes in the value of zeta over this entire range of zeta varying from 0 to 0.9, which mostly covers the entire range of underdamped responses. Okay. So therefore, again for the sake of simplicity and because we do not want to remember too many different values, people generally settle for a settling time of 4 by zeta omega n. Now notice the settling time therefore is inversely proportional to zeta omega n. And what is zeta omega n? Now again let me go back to that earlier slide where we had derived these. What is zeta omega n if zeta is less than unity? It is after all only the real part of the pole, alright. So what then this means is, and it is quite meaningful also, it makes sense, because you see what we are saying is that the settling time here, the settling time is dependent as if solely on this zeta times omega n, which is the real part of your complex poles. That makes sense because it is after all only this real part of the complex pole which is affecting this envelope, and we derive the settling time by considering only the envelope. So it then stands to reason that the settling time should depend only on the real part. Okay. So that is why it is an easy way to remember. We have considered the envelope to derive this. The envelope is dependent only on the real part of the pole, and therefore the settling time is also dependent on the real part of the pole. Okay. So in fact, so much so that this real part of the pole is also often, after all it has the units of frequency, it is also called the Neper frequency. So when you have the imaginary part of the pole, that can easily be correlated with some frequency of sinusoids and cosinusoids, but this real part, it appears as part of the real exponential. So you do not generally think of this as some sort of a frequency, right, but it turns out this is also called a Neper frequency, and this basically dictates how soon your transients are going to decay. Just like your ordinary frequency that we understand it to be dictates how many times the oscillations will occur within a given time frame, within a given time period, right. Similarly, this also tells you how fast, so how many times means how fast the system oscillates, right. So that is basically the imaginary part of the pole, but the real part of the pole tells you how fast the transient response decays, and the settling time also tells you exactly that. So it is really not a coincidence, right, that the real part of the pole, which also has the dimensions of frequency, actually tells you how fast your transient response settles down. So notice you might think that okay, rise time is telling me how fast the system responds, the transient is also telling, the settling time is also telling me how fast the system responds. So what is after all the difference? There is a difference if you notice carefully. You see, the rise time is actually telling you how fast your system responds to the application of an input. In other words, if you have applied a step input, how soon a system responds and rises in response to the application of that input. Okay, so that is one measure of speed of response. On the other hand, the settling time tells you another, it gives you another measure of the speed of response. What is that? This is telling you how soon you basically settle down. So how soon your transient oscillations kind of decay to insignificance. Okay, so although these are both telling you how fast your system responds, they are basically two different notions of how fast a system responds. I want you to bear that in mind. So do not make the mistake of thinking that rise time and settling time have the same connotation. They really do not. Okay, both from the interpretation of the pole itself, we've seen the rise time depends on the magnitude of the pole, the settling time depends on the real part of the pole, right? And also physically speaking, one tells you how fast a system responds to the application of an input, which is the rise time. The other tells you how fast the transients decay and the system kind of settles down to a steady state. Okay, that is the settling time. Alright, so these were not very easy to describe when we were only talking about first order systems, but now with second order systems, I hope that you begin to see the connection and the reason why we have these two different metrics, okay, independent of one another, the settling time and the rise time. Okay, so the next thing we are going to derive is basically going to be the percentage overshoot of the system. Okay, so how are we going to derive the percentage overshoot of the system? Actually at one go we will not just derive the percentage overshoot, we will also derive the peak time. So again, let us go back to this plot here. Basically we've shown you that the peak time is the first time, of course subsequent peaks and troughs are smaller, right. So the first peak is actually the largest peak, we know this from our plot. Of course if you are not very convinced, you can obviously try the usual differentiation technique and also take that second derivative and see that the second derivative is indeed, if it's indeed going to lead to a maxima, then the second derivative is going to be negative. So you are welcome to try that as part of an exercise. In fact you should actually convince yourself, although it's pretty laborious computation, so I will not undertake that second derivative computation, but for the sake of completeness you should then find out that first y dash t is equal to 0, you should solve for t to get Tp. So I am going to do this, but then in order to convince yourself that this Tp is indeed corresponding to a maxima, you should then also obtain y double dashed t at Tp and check if it is negative. Okay, so this is part of an exercise that you should do and convince yourself. The first part I will do, although even while I am doing the first part I will not really explicitly differentiate because I can do better. I know Laplace transforms, I know that differentiation in time domain is tantamount to multiplication by s in the frequency domain, so I shall not actually undertake the task, the onerous task of differentiating this. What I shall instead do is I shall take the Laplace inverse of s times the step response. Okay, so I again leave it to you to check that y of s is given by 1 over s upon omega n squared upon s squared plus 2 zeta omega n s plus omega n squared, right. Therefore s times ys, right, is equal to nothing but omega n squared upon s squared plus 2 zeta omega n s plus omega n squared, which is nothing but omega n squared upon s plus zeta omega n whole squared plus omega n squared times 1 minus zeta squared, right. So this we are already familiar with, we did this in the previous lecture, we have seen this, alright. So now of course we are going to have to massage this into the form that we desire. So we are going to pull out 1 omega n and stick up this 1 minus zeta squared with it in the denominator, and then we will have this standard form from which we can read off directly from the inverse Laplace table, right. So now we have omega n times root 1 minus zeta squared whole squared, alright. So hang on, there will be a correction here, this adjustment with 1 minus zeta squared under root, and yeah, now we are set. So therefore we know that Laplace inverse of s times ys is equal to nothing but y dashed t, which is going to be nothing but I'm going to just write down that expression here, omega n over root 1 minus zeta squared times e to the minus zeta omega n t sine of omega dt. Okay, so we are going to equate y dash t to be equal to 0, which further leads to the fact that omega dt, of course this, as I told you, only goes to 0 as t tends to infinity, so we discount this. So the only way that this can go to 0 is if sine omega dt is equal to 0, or in other words omega dt is equal to n pi, where of course n can be any integer value, so on. So we are only going to consider the first peak, alright. So we are going to plug in n is equal to 1, n is equal to 1 is what we are going to plug in, and we get then that t is equal to, so this is basically the peak time is going to be equal to pi upon omega n square root 1 minus zeta squared, alright. So we have derived this, no approximations here thankfully, completely analytical expression. And the good thing is, again notice, let me take you back a few slides where we derived those roots. Again notice that this is nothing but inversely proportional to the imaginary part, okay. So the peak time is actually inversely proportional to the imaginary part of your pole, alright. So we are very nicely being able to isolate the different parts of the different performance metrics with different parts of the pole and see their dependence, and that is one of the main purposes, one of the chief purposes of this analysis and this study, alright. So this is our Tp. Now as we have derived Tp, it then turns out that the derivation of the percentage overshoot, so let me first define the percentage overshoot. I have probably not defined this carefully enough. So the percentage overshoot is defined as Ytp, which is basically the maxima, the first maxima. So again remember, to reiterate exercise, check that this is a maxima, okay. So in order to check that, you will have to take the second derivative. So you can either take s squared times ys, or you can do the usual differentiation and check that it is indeed a maxima. As I said, you will have to check this, that y double dash at Tp is negative, right, in order for this to be a maxima. Okay. So now the definition of this percentage overshoot is given by Ytp minus Yss, which is the steady state value of y, okay. So this is not necessarily unity, do not make this mistake. It has nothing to do with the amplitude of the input signal, okay. It is basically the steady state value of the output. So for example, if your gain of the system is 0.7, then your steady state value will be 0.7. If your gain of the system is 70, the steady state value will be 70. Do not compare this with 1 by default, okay. So it is the peak value minus the steady state value divided by the steady state value into 100, alright. So now that we have already derived this Tp, why don't we just plug this Tp into our well known expression for the second order response. So we can just plug in Tp instead of this T here and Tp instead of this T here and find out this y at Tp, alright, which is basically this value, this peak value, alright. And then we can subtract Yss, which in our case is unity. As I said, in general it is not unity, it will be subject to the gain of the so called DC gain of the system. What is the DC gain? When you plug in s is equal to 0, it is a DC gain of a system. Just as an aside, why is it a DC gain? Recall, maybe a couple of lectures back or a few lectures back we had shown you that if you have g of s, alright, and if you apply to it an input of the form e to the alpha t, alright, then the output yt is given by, so the small yt is given by g of alpha times e to the alpha t. Now suppose this alpha is 0, okay, suppose this alpha is 0, what happens then? Then your response is going to be nothing but g of 0, no, right. So what is alpha 0 corresponding to? Alpha 0 corresponds to a constant input, which is like a DC current, application of a direct current, a constant value of current. So therefore this is called the DC gain of a system, okay. Alright, so having seen that, you now are convinced, at least I hope, that this g of 0 is the DC gain. So of course if the DC gain of your system is changed, then your steady state value will also change, right. So therefore it need not be unity always. In our case we have normalized it, so it is unity, okay. Do not make that mistake, that is another crucial aspect to remember. Alright, so now without much effort we can actually see that if you plug in this value into this expression for the second order response that we derived in the previous lecture, what happens? You see, you apply this t as pi upon omega n into root 1 minus zeta squared. So this omega d and omega d cancel out, alright, yeah. So this is just cos pi minus phi. So what is cos pi minus phi? Okay, let me just write it down and not just do it in a hand waving fashion. So y of Tp is nothing but 1 minus e to the minus zeta omega n. Tp is pi upon root 1 minus zeta squared omega n. Yeah, we have already seen that, times, so of course you have 1 minus zeta squared here, times cos of omega n root 1 minus zeta squared, that is what omega d is after all, and then we plug in the value of this, yeah. So that is what I was talking about, this omega n and omega n cancel, this 1 minus zeta squared and 1 minus zeta squared cancel. So this is cos pi minus phi, alright. So I am ignoring the, okay, let me not ignore it, let me write the unit step, it does not really matter. So what then this turns out to be is the following, 1 minus e to the minus zeta omega n, okay, this also cancels out, so let me not carry this baggage for so long. So this omega n and omega n cancel out, so this is minus pi zeta over 1 minus zeta squared times, what is this? This is cos pi minus phi upon square root 1 minus zeta squared. But what is cos pi minus phi? Yeah, is it not just equal to minus cos phi, right? So this is going to be equal to 1 minus e to the minus pi zeta upon root 1 minus zeta squared, then this is, of course that minus sign will change, so this is going to be cos phi upon root 1 minus zeta squared. But notice cos phi is nothing but itself 1 minus zeta squared, so this cancels out, right. So therefore what we are left with is 1 plus e to the minus pi zeta upon root 1 minus zeta squared, right. So therefore percentage overshoot turns out to be y Tp minus y Ss upon y Ss into 100 is equal to 100 times 1 plus e to the minus pi zeta upon root 1 minus zeta squared, yeah, minus 1 over 1. So this 1 and 1 cancel. So in other words, this just turns out to be 100 times e to the minus pi zeta upon root 1 minus zeta squared, okay. So now notice that percentage overshoot is just a function of this zeta, but what is this zeta in the context of the poles that we have derived? Maybe again I revert to this derivation here. What is this zeta? You see, this ratio of the imaginary part to the real part, yeah, this ratio of the imaginary part to the real part is also a function of zeta, okay. So let me go back now. So we observe that, so this is an observation. So observation is that ratio of imaginary part to real part of pole is a function of zeta alone. This is observation 1. Observation 2, percentage overshoot is also a function of zeta alone, right. So therefore based on these two observations we may now conclude that percentage overshoot, because we see every performance metric we are trying to connect it with some feature of the poles of the second order system. We've seen that the peak time is related to the imaginary part of the pole, the settling time is related to the real part of the pole, the rise time is related to the magnitude of the pole. Yeah. So now we see that this percentage overshoot is similarly related to the ratio between the imaginary and real parts of the poles. So if you keep the ratio between the imaginary and the real parts of the poles fixed, you are keeping the zeta fixed. If you are keeping the zeta fixed, you are keeping the percentage overshoot fixed. So if you now draw, so this is what we are going to do next, we are now going to draw certain loci, certain locus on the complex plane, and we are going to always qualify them by the kind of metrics that they specify. Okay. So notice now, so let me go to the next slide, and this is what we are going to do. So first, what is the locus of all points, yeah, on this complex plane? So this is basically the complex plane, this is the real part, this is the imaginary part. Some people write this as r and this as j times r, it's basically the same thing, alright. So it's the argand plane. Now notice that if you want to draw the locus of all such points, yeah, whose magnitudes are constant, it's going to be a part of a circle, but remember we have only dealt with systems which are stable, whose poles are on the left half plane. So therefore we are only going to deal with a semicircle like this, yeah. So this is locus of all poles with constant magnitude, okay. So if you have a pair of poles here, the magnitudes of these fellows is given by this radial line, this radius. If you had a pair of poles here, the magnitudes of those will also be the same, even if they are not identical poles. These two pole pairs are certainly not one and the same, but notice that their magnitudes are still the same, okay. So that is crucial, alright. But what does this also determine? See, we have also said that if the magnitudes of the poles are the same, then their rise times must also be the same. So this is not just a locus of all poles with constant magnitude, this is also a locus of all system poles that lead to same value of rise time, alright. So this is not just a magnitude of constant magnitude pole locations, but this is also a magnitude of constant rise time. So now what we are doing is, for an audience who is not very technical, after all remember we are going to specify our system metrics in terms of rise time, peak time, percentage overshoot, settling time and so on and so forth. So a user will tell you, I want a rise time of this, I want a settling time of this. The user will not tell you that I want a pole location at this point. That's for you as a control engineer to determine. So given that that is the situation, the moment a user tells you that I want a certain value of rise time, you can immediately draw this locus on the complex plane and say that okay, so that means the user is telling me to place my poles on this particular locus, somewhere on this semicircular arc, okay. That is the job of the control engineer. That is why we are interested in translating these performance metrics to their corresponding pole locations on the argand plane, alright. Now next, let's talk about, let's say the peak time. So what do we know for the peak time? What are the loci of constant imaginary poles? Yeah, those loci are going to be like this, no? Yeah. So you consider a pair of poles here and you consider a pair of poles marked by the red ones here. Of course these two poles are not the same, but notice that their imaginary parts are still the same. for both these pole pairs, and if their imaginary parts are still the same, so this is a locus of all poles or pole pairs rather, because these are complex, with same imaginary parts. But no sooner do we observe that this is the locus of all poles with the same imaginary part, can we also deduce or infer that these are also the locus of all second order systems poles corresponding to the same peak time. So in other words, we now translate it in our parlance as locus of all system poles that lead to same value of peak time, alright. Okay. So notice that this rise time, this is also valid not just for underdamped system but also for overdamped and critically damped system. Of course, in such case you will be only confined to this real axis, so you will have poles somewhere here, okay. So this is for, let us say, a critically damped system when you have repeated poles and you then consider this to be the rise time approximately, okay. Yeah. So I just wanted to put that point as an addendum of sorts. So the next feature that we look at is, let us say, a settling time, okay. So what is the settling time related to? We have seen that. Now let me draw this JR here and this R here, again the Argand plane. Now notice that the settling time is dependent on zeta omega n, which is nothing but the real part of the pole. So what is the locus of all poles which share the same real part? It is going to be like this, a vertical line. So again, to refresh, notice that this pole pair marked in red and this pole pair marked in green, they are different, they are distinct poles no doubt, but they both share, both these pairs, the red and green pairs, they both share the same real part, alright. And by virtue of sharing the same real part, they also give rise to the same value of settling time, albeit approximate, let us not forget that. But once we agreed upon the fact that this is going to be our settling time, we know that this locus, okay, so this is what? This is in the same fashion as we wrote here, this is the locus of all poles with same real part, okay. So you specify one such locus, you specify another real part, you draw another parallel vertical line, just like here also for different specifications you draw different parallel horizontal lines. Here for example you draw different concentric circles for different values, right. So here for another value of this rise time you will draw another locus like this, for a smaller rise time you will go right to upwards like this, for a larger rise time you will come inside like this. Similarly here also for smaller values of peak time you will go up, for larger values of peak time you will come down, but draw parallel lines to this. Similarly here, this is also the locus of all system poles with same settling time. So this is basically the constant settling time locus, just like this is the constant rise time, peak time locus, and this is the constant rise time locus, okay. Alright, so this is the locus of all systems poles with the same settling time, okay. So notice again a point, if you have a critically damped or an underdamped system, then of course you will have only real poles. So this is just as an aside, let me make a small box here. So suppose you have a pair of poles like this for an overdamped system, then how do you determine the settling time? Okay, it turns out that then the chain, just like we talk about this, a chain is as strong as its weakest link, so also a system is as fast as its slowest mode. So which pole do you think out of these two is going to be the slower of the two modes? Of course the one that is closer to the origin. So if you have a pole pair corresponding to an overdamped system like so, then in order to evaluate the settling time, you consider the pole that is closer to the imaginary axis, yeah, and then take 4 times. So if this is P1 and this is P2, then you take 4 by P1 as your settling time, okay. So I just wanted to put that discussion to rest, because you might wonder that there also should be a settling time expression or a value for overdamped systems, and you might be confused as to what should that be, because there are now 2 distinct poles, because for complex poles both these poles will have the same real part, so we do not really care, yeah, they will both have the same real part and opposite imaginary parts, opposite in sign. But for a real pair of poles, which is an overdamped system, right, you have 2 distinct real poles. So which is the one that should govern this settling time? It is the one which is closer to the origin, which is also called the dominant pole, because the rate, this is the rate determining step, this is the pole which governs how fast your system responds, alright. So keep that in mind. So even if you encounter an overdamped system, you can still define the settling time as a reciprocal relationship with respect to the pole location if you consider the dominant pole, okay. So hopefully that settling time discussion is now clear, and you also know the constant settling time loci here, okay. Finally we come to this discussion about the percentage overshoot that we have discussed. So what are these percentage overshoot loci? Now let us look at this expression for percentage overshoot here. What did we see? It depends on zeta, but what does zeta govern? Zeta, you see, after all governs only the ratio between the imaginary part and the real part. So what is going to be the loci of this zeta? Yeah, zeta governs the ratio between the real part and the imaginary part. So therefore if you take any pole here for instance, yeah, and if you take the ratio between the real part and the imaginary part, it is basically this ratio to this value, which is basically going to determine this angle. So therefore if you want to determine a constant zeta line, let me erase that part now. So if you want to determine a constant zeta line here, it is going to be these radial lines like these, right. These are going to be your constant zeta lines, constant zeta loci. So these are, so you have again in the same fashion, if you have a pair of poles here and a pair of poles here, then both of these poles, again both of these pole pairs are distinct, but they still share the same zeta, and by virtue of sharing the same zeta, so these are all locus of all poles with same real part, real part to imaginary part ratio, yeah, because this constant line shows that the ratio between the real part and the imaginary part along this line is constant, or in other words this is the locus of all system poles with same value of percentage overshoot, that is what this is, yeah. Suppose you encounter a user who tells you that look, I want a rise time to be lesser than this, okay. So immediately you draw that bound on the rise time, so you draw a semicircle, and you know that any pole that lies to the left of this sector here will meet the rise time specification, okay. So this is the rise time specified. Now the user tells you, I want my percentage overshoot, yeah, to be less than this percent, okay. So you immediately draw this percentage overshoot loci, the constant zeta line, and you know that anything that lies within this sector, okay, anything that lies within this sector is going to satisfy that. So remember, if you go outside of this, then you are going to violate the percentage overshoot, because as you move this line, as you rotate this line in this direction, you are basically decreasing zeta, and if you are decreasing zeta, your percentage overshoot increases. Now of course maybe that is a point I have not discussed enough, But you notice here that if you increase your zeta, if you increase your zeta, then pi zeta increases in magnitude, and 1 minus zeta square decreases in magnitude. So this overall thing increases, and this is e to the minus, so this is headed by a minus sign here. So this overall e to the minus pi zeta by root 1 minus zeta square actually decreases with an increase in zeta. So if you increase zeta, you are basically coming in this direction, and a decrease zeta. So this direction is zeta increase, this direction is zeta decrease. You can take this as an exercise to check that it is indeed so, alright. Okay. So now, because the reason being quite simple really. So because this is your angle phi, sine inverse phi is zeta, sine inverse zeta is phi, right. So as you increase your phi, the zeta will only increase, because sine is an increasing function in that range from 0 to pi by 2, right. So then you have now located these two. Now suppose they also say that I want a settling time to be smaller than this. So then you draw this sort of a vertical line like this, and you notify and you identify this region to be your tentative pole location. So combining all of these, you now require an intersection. So then the net result is you draw a constant TR loci, you draw a constant TS loci, alright, and you draw a constant percentage overshoot loci, like so. And you know that any pole which lies within this intersecting region to the left of all of these and within this sector, any system whose poles lie within this will meet all of your three requirements. This is the percentage overshoot, this is the settling time, this is the rise time, okay. So this is how you identify where your system's poles must be. So as a system designer, you have now been able to translate the user's specification to a nice location of the poles, okay, a relatively nice location of the poles. Now it is your job to design a system or to shape a system in such a manner that the poles of the shaped system lie within this region that I have marked with red ink here, okay. So we will talk more on this in the forthcoming lectures. For now, this is a good place to stop.